Hello guys, welcome to another CNCM lecture, and today's topic is going to be basic functional equations. My name is Eli Park and the day of recording is October 26th, which just happens to be my birthday. So let's get started with this introduction. So, functional equations are problems that will ask you to find all functions that satisfy a set of conditions. In most classic functional equations, there's going to be two conditions. So the first condition is normally going to be a domain and range of the function. So for example, if we say, for example, f colon r to q. So what this means is that f has a domain of real numbers, which is denoted by this r, and then it has a range of rational numbers denoted by this q. So you can think about it like this. F maps real numbers to rational numbers. That's basically what this notation is saying here. Also, a problem could say, for example, solve over positive integers. So we know that positive integers is denoted by n. So what we could this is saying solve over positive integers is equivalent to writing f maps n to n. This is the same thing. So the second equation, or second condition, I should say, is going to be an equation, which is going to be the heart of the problem. So, for example, the equation from the functional equation from the USEMO problem 4 2020 is f of, I should get my pen out, f of x plus f of y plus xy equals to x f y plus f of x plus y. So yeah, this basically means that for every function f that is a part of the solution has to satisfy this equation for every valid x and y. So yeah, so the actual parts of this is not important. We're going to learn how to extract the function from this equation later on, but just know that this is what an example equation could look like. So all functional equations are two-part problems. So this means that not only must you find all working solution functions, meaning that you need to cut out what are not working functions, you must have to then confirm that those list of functions that you claim may work actually work. If that's a little confusing, let's say you have a group of a bunch of marbles, like maybe you have some blue marbles, and then you have a bunch of red marbles. Let's say those dots are all marbles, okay? So then let's say someone tells you to go hey, get all the blue marbles. But maybe you can't see, maybe you're colorblind, you can't see the blue marbles. So what you do is just you see these red marbles and you know they're not blue, so you take them out. And you're left with the blue marbles. But the thing is that since you're colorblind, you did know that those red marbles, that you take them out, but you're not actually sure that these marbles in here are actually blue. So that's kind of what's happening here. We have to verify that they actually work by checking that these marbles are actually blue, or these functions that we claim work actually do work. So for example, in our earlier thing here, the solution to this functional equation, is f of x is equal to x. Well, how can we actually check that? We can just plug it in. So for example, this f of y right here, if we plug in our solution, then that just simplifies to y. So I'll just unwrap it. So just take out the f in the parentheses, oops. And then we can just unwrap everything. So basically, this f of y here to the right, we can just get rid of this because it just becomes a y. This f of x plus y just becomes x plus y. And this f on the very left, this big one, we can take it out. And what we're left here is just a true statement. Like, there's just nothing to say about this. This is just a mathematically sound statement. So that's how we check that it actually works. So now let's get going with some definitions. These are just some definitions, the sets of numbers that we use in our notation for our function, domain, and range. And these definitions are a little more important. So we want to know if a function is injective, surjective, or bijective. So an injective function is if f of x is equal to f of y if and only if x equals y for all x and y. So in other words, this means that it is a one-to-one function. So basically, if you drew to one of those like charts where you have like a set A and a set B, and you have like elements 0, 1, 2, 3, 0, 1, 2, 3, right? Let's say and you have a function. So let's say maybe 0 maps to 1. Then that means that none of these numbers, 1, 2, and 3, none of them can map to 2. Wait, did I say it was 1 or 2? Let's say that this is 0, 1, 2, the 1. I forgot what I said. Then that means that none of these numbers, 0, 1, or 2, none of them can map to 1. Because this is not allowed, because this is a one-to-one function. Only one number in this range is allowed to pair, actually only one number in this domain is allowed to pair with a particular number in the range. So in other words, to just sum it up, it's a one-to-one function. A function is surjective if for each a there is some x such that f of x is equal to a. So basically what this means is, in other words, this means that like the function reaches the entire range. So like if you just plug in every value of x, you're gonna eventually get every single number in that range. It's all reachable, I kind of want to say. So if you have like that notation earlier where we had like 0, 1, 2, 3, well not notation, but that example. A surjective function, for example, this would be a surjective function where 3 goes to 0, 2 goes to 2, 1 goes to 3, and 0 goes to 1. This is a surjective function because every single number in this range has an arrow, meaning it can be mapped to. But for example, if I had, maybe this goes here, and this goes here, this goes here, and that goes there, we see that these 2 and 3, nothing goes to them. So that means that this function is not surjective because not all things in the range can be reached. So a function is bijective if it is both injective and surjective. So that's fairly straightforward once you talk down what injective and surjective functions are. Okay, so let's get started with some basic tips. So in functional equations, you want to first thing you want to do, or maybe not necessarily first thing, but something that you almost do in every single standard functional equation is that you want to find the answer, or at least guess what it is with a high degree of like how you're pretty sure that you have the right solutions. So for most standard functional equations, the solutions will all be linear functions. It will also normally be obvious when they aren't. So for example, if you have f of x times f of y is equal to f of x plus y, clearly this is not linear. And you can see, for example, f of x is equal to e to the x works. It's not all the solutions, but it works. Something along those lines. It was pretty obvious when it's not. So if it's necessary, you may have to plug in higher degree polynomials, maybe 2 or 3. It can't get that big unless maybe it's of the form like f of x is equal to x to the k for some large number k. I don't know. There are a lot of different functions that it could be, but there's actually not that many. Like in terms of variety, most of them will be linear functions anyways. Second tip is that you want to think about the domain and range. So if your functional equation is over rationals or integers, for example, there's probably a reason why that problem wasn't over reals. Because if there was no reason and that the problem was perfectly fine over reals, they would have probably given it like that. So maybe this is a hint that you want to induct, because you can't induct over reals because there's for example, integers. There's a finite number of integers in a finite range, for example. So you could hypothetically do an induction, which may not work on rationals or reals. Or maybe you could do something with rationals that you can't do with reals. It's just that idea. So the third tip is you want to just plug stuff in. Plugging in stuff, just stuff. Like I gave 4 examples here: 0, y, 1y, f of x, etc. But you can plug in anything that may give some simplifications. These are going to give you clues going forward. Okay. And the fourth tip is that you want to keep in mind that proving that f is injective and or surjective is very useful and can help solve most problems if you were able to get to that proof. But do note that this is not actually possible. So like you may look at a problem and you're like, hey, if I can get that this function is surjective, then I'm done. But then there's a solid chance that you're not actually going to be able to get that function is surjective directly. So let's move on. So let's get started with our first example, okay? Let's get going. So here's our first example, okay? So find out functions that such that f map natural numbers to natural numbers such that f of n plus f of n squared is equal to n squared plus 3n plus 3, okay? So, going back to our tips earlier, the first tip was to find the answer. Find the answer. So, we first want to find all linear solutions here because those are probably our best bet. So, let's write in f of n is equal to mn plus b and see which constants m and b satisfy this equation, okay? So by plugging it in, we get m times mn plus b plus mn plus b squared is equal to n squared plus 3n plus 3. See that? We just straight plugged it in. And then we'll just expand this. We have m squared n plus mb plus b plus m squared n squared plus 2mnb plus b squared is equal to n squared plus 3n plus 3. This looks getting a little messy, but trust me, it's actually fine. Once we expanded this, what we do need to notice is that m and b are constants, but n is not. So we want to find and match like terms. So for example, we see that there's only 2 n squared terms. There's the one here and the one here. Well, if they have to match, then that means that m is going to have to equal plus minus 1, or else it won't match, okay? So we want to test both. So let's try plugging in m equals -1, okay? If we plug in m is equal to -1 into here, we're going to get that this first term becomes just n, and then it becomes minus b plus n squared minus 2nb plus b squared is equal to n squared plus 3n plus 3. And then we see that we get some simplifications now. This minus b plus b cancels out, and then the n squares on both sides cancel out. So wow, we actually have a lot simpler. I'll move this n over to the right side. We actually have a lot simpler equation now. We also can match up the constant terms now that we have the n squared terms out of the way. The constant terms, we have b squared and 3. But wait, right now that's an issue, because if b squared is equal to 3, then that means b is not going to be an integer. And that's a problem, because f of n is equal to mn plus b, and our output must be integers. If b is and a non-integer, we're gonna have problems. So we know that there's gonna be no solutions here. We can't have any b that works. So that means that when m is equal to -1, which was our assumption here for this part, we're not going to have anything. So now let's just start assuming that m is equal to 1 and see what solutions that gives us. So if we get m is equal to 1, very conveniently, I'll just erase every instance of m because that's just the same thing as plug in m equals 1. So yeah, now we'll do a little bit of simplifications. Yeah, so the n squared terms, they cancel out, so I'll get rid of the n squared terms on both sides. And then we also see that there's an n and a 3n on either side, so we'll do some simplifications there. So this n will go away and this will become a 2n. We have a lot of simplifications. The b plus b will become a 2b. So yeah, what we have here is now that we have two n terms. We have this term and that term. We want to match that up. Matching that up gives us b is equal to 1. So now we have m equals 1, b equals 1. And we want to see if this holds. So if we plug in b equals 1, this goes away, and this can't go away. We still have to replace it with a 1. And then we see here that these are actually equivalent statements, because 2 plus 2n plus 1 is in fact equal to 2n plus 3. So that means that m equals 1, b equals 1 is going to be a solution. And in fact, that is going to be our only linear solution here. So yeah, now we want to go about proving that this is the only solution. But we could do a little investigation to see if there's any other solutions, but what we're going to get, just a little spoiler alert, this is going to be our only solution, where m equal 1, b equal 1. So basically, f of, let me write in black. So f of n is equal to n plus 1 is going to be our solution. Now we want to prove that that's the only solution. Okay, so let's get going. Actually, let me just clear all ink in here. So, okay, so if this guess is correct, where f of n is equal to n plus 1, then we could try to use a general motivation. So right now what we have is that we just have one solution, okay? A lot of times functional equations, they'll have like maybe f of n is equal to x, where, oh wait, oops, it should be f of n equals n. Well, a lot of times functional equations are going to have multiple solutions. Like for example, f of x is equal to x and f of x is equal to 0 are going to be solutions maybe. But the thing is that right in here, in this case, we have only one solution. So what we can do is that we could try to use the general motivation behind the unproven fact that every value must map to only one value over all possible solutions. So if we have like f of 1, right, there's just going to be one value over all possible solutions of x. There's only one possible value of f of 1, which we want to guess that is 2, but we actually need to start going about proving that, because right now all the work we did is actually just a guess. So since we're over positive integers, we have a lower bound. We know that 1 is our smallest number that we can plug in, okay? So let's see what happens when we plug in 1, okay? Let's just see what happens. Let's plug it in right here. We have f of 1 plus f of 1 squared is equal to, this becomes 7 if we plug in 1. Okay, so at first glance, there doesn't seem to be anything special. I just plugged in n equals 1, right? But this actually helps a lot right now. Why? So we can see. What? Can we find f of 1 here? That's what our goal is here. And yes, we can. If we plug, we know that f of 1 can't be 1. Why? Because if it was 1, then this f of 1 would just simplify to 1. This f of 1 squared would just simplify to 1. 1 plus 1 is not equal to 7. So f of 1 can't be 1. That's just not true. So we also know that by a little bit of experimenting, f of 1 cannot be greater or than or equal to 3. Because if it were, then this term would be greater than 7. And then this term has to be positive because by definition, the range has to be all positive numbers. So that means that this entire portion would have to be greater than the right-hand side, meaning which is a contradiction because they have to be equal. So f of 1 has to be less than 3. But what does this tell us? Should be not a plus minus, but a not equal to. What this tells us is that f of 1 is just equal to 2. And yeah, f of 1 is equal to 2. So that's the first step. We now have actually proven that f of 1 is equal to 2, and this is not just a guess. And in fact, we can see that this lines up with our hypothesis. So we have we've tacked down f of 1 is equal to 2. So now, give me 1 second. Okay, so now it's natural to ask, can we find f of 2 explicitly, like we did to f of 1? There is yes, the answer is yes. That's what we want to try to do. But there is a messy way to do this if you plug in n equals 2 into this equation. But the thing is, there's actually a much easier way right in front of our eyes when we found f of 1 is equal to 2. Plugging n is 1 back into the equation, we have f of 1 plus f of 1 squared is equal to 7. But we know that each instance of this f of 1, that just becomes 2. So this becomes 2. This becomes 2. Oh wait, this looks simple. We just have f of 2 is equal to 3. So we're getting somewhere now. We've it looks like we're getting somewhere, and this was actually very quick compared to our f of 1. So yeah, the reason why we were able to do this so quickly is that there's so many instances of f of n here. There's 2 instances of it. If we know one value, which we know f of 1 is equal to 2, plugging that in will give us immediate simplifications. So now we want to use this idea to help us prove that the entire function f of n is equal to n plus 1, not just for these 2 particular values. So what can we do? So now we want to use our knowledge of f of 2 to find f of 3. Well, maybe we could plug in n equals 2 in this equation. Well, we'll have f of 2 plus f of 2 squared is equal to 2 squared plus 3 times 2 plus 3, which is equal to 11. So we see that if we just plug in f of 2 in our definition, this just becomes f of 3 is equal to 11. Actually, no, that's not 11. That should be 13. Silly me. This just becomes 13 minus 2 squared, which is 9. I mean, sorry, f of 2 squared, which is 9. So this becomes 4. So now we have f of 3 is equal to 4. It's now very convincing that this is our only solution, or if it was not already convincing. But now, what else do we notice? We see that we're starting to get some sort of pattern. We're using one piece of knowledge that we have to find the next, and then we use this piece of information to find the next. That's very familiar. That sounds just like induction. So maybe we could actually try induction. So maybe we want to do, for example, maybe we want to claim that f of n is equal to n plus 1 for all n. And we already have a couple base cases. We already know that f of 1 is equal to 2, f of 2 is equal to 3, and f of 3 is equal to 4. But we want to try an inductive step. So let's say that our claim works where n is equal to k, okay? So that means that we know that f of k is equal to k plus 1. We've already proven that, okay? We want to prove that our claim works for n equals k plus 1. Meaning that we want to prove that this works, that this claim is true given that. Well, how can we do that? We'll use this idea and we'll just plug in k into n in this functional equation. We'll plug that in. We'll have f of k plus f of, oh shoot, that should be a double f. F of k squared is equal to k squared plus 3k plus 3. Then plugging in what we proved, f of k is equal to k plus 1. So we have f of k plus 1 here plus k plus 1 squared is equal to k squared plus 3k plus 3. Oh wait, we can just expand this and then put it over there. Simplifications give f of k plus 1 is equal to k plus 2. Oh wait, that's exactly what we wanted. So our inductive step is actually complete. So now we're done because we've actually proved that now that if once we have f of 1, we can find f of 2, and then if we have f of 2, we can find f of 3, and we've proven that we can keep going into infinity, which proves our claim that f of n is equal to n plus 1 actually works. So this is what an actual solution would look like. Note, there are some things that I do want to note. So in this solution, we just have a claim, which I say clearly works, and then we have the induction. Note what we're missing. One big thing we're missing is that I did not contain the entire process where we guessed the solution. We just said it. Like, we just said it right here. There's no, in the top right here. There's no need for us to go through that. Because it's actually just, it's just generating clues. Also, we didn't actually explicitly go through f of 2 or f of 3. Those are only things that we tried to help us realize that induction is actually a viable method. The only thing we actually need to go through manually was f of 1 because we need to generate a base case for the induction. So like right up, yeah, that part. Okay, so now let's get going. So now let's look at the f of x is equal to x lemma. It's fairly, it's not extremely important, but it's actually very, quite instructive in my opinion. So we want to prove that if we have f of x is equal to x, then f is a bijection. And remember that a bijection means that the function is both an injection. Can we say that? F is injective and f is surjective. So we want to prove both. So first we want to prove that it's surjective, okay? So clearly, x can be anything, right? So that means that f of x, so if we write this down like this, since x can be anything here, right? This can just range from anything, it just can be anything that we want to make it. That means that this f of something, which just happens to be another f of x, is gonna have to equal that number, meaning that this function f right here is going to be able to reach all values. Right? So that means that f is surjective here. That was kind of a weird way to put it. It would be a little bit weird as a word, but what the gist here is that we have f of something here, and that something is not greatly important. But that f of something is going to equal x, and x can literally be anything. It can be anything, meaning that f is surjective because f of something is going to equal that anything. Now we want to prove injectivity, okay? This is a little harder, but bear with me. So let's say, for the sake of contradiction, that a and b are numbers such that f of a is equal to f of b, except a is not equal to b. If two numbers actually existed, this means that the f is not injective. So we want to run into a contradiction here. So since we know that f of a is equal to f of b, we can just apply another f around them. Actually, no, let me not write it there. You can just apply another f. Oh gosh. We can just apply another f around them to get f of A is equal to f of B. But in fact, we get that f of x is equal to x, so that means that we can let f of A be equal to A. But then we can also put here that this is equal to B, because f of B is equal to B. This is a contradiction. A is equal to that, which is equal to that, which is equal to that. A cannot be equal to B by our that. So that means that our function is indeed injective. Okay, so now let's look at one final example, okay? This is from the IRAN TST 1996, okay? This is a very instructive problem, and we're going to divide this problem into two parts, and each are quite important in my opinion, okay? Let's look at this problem. Okay, yeah, the cancellation trick, okay? The cancellation trick. So this trick is summarized nicely by a quote from an Evan Chen handout. Durr, we want stuff to cancel. Well, how can we do that here? We want to attempt a very rude cancellation by letting stuff be equal as barbaric as possible. So how can we try that? Maybe we could let we want maybe this term and that term to be equal. If those are equal, then those would cancel out, and that would be actually very nice. But can we actually pull that off? Actually, we can. All we need to do is that we just need to let this inside part be equal. So if we let x squared plus y is equal to f of x minus y, then we're cool. But the thing is that we can actually do this. We can just plug in y is equal to 1/2 of f of x minus x. If we plug this in, then this actually automatically cancels. So let's actually try that. So this is actually very helpful now. If we plug in, let me write this up here, y is equal to 1/2 f of x minus x. We can see that plugging this in for value of y is going to cancel out these two terms. So you're going to have 0 is equal to 4 times f of x times y, which in the specific example that we plugged in was 1/2 times f of x minus x. I should put that in parentheses, okay? So the 4 and the 1/2, they can just disappear, okay? So this is actually very nice looking now. We have 0 is equal to f of x times f of x minus x. If you had went through the guessing process, you would have seen that f of x equals 0 and f of, I apologize. Okay, this entire time this should have been x squared, okay? This should have been x squared. That didn't affect any major details, but that should have been x squared. So, okay, so if you had gone through your solutions, you would have gotten that the solutions were probably going to be f of x equals 0 and f of x is going to be x squared. From first glance here, if you might look like we might be done. This doesn't look like, this looks like, f of x is going to be 0 here, or f of x is going to equal x squared here. So it looks we're done. And you may be right. Actually, wait, not yet. You have now fallen into the deep, dark, pointwise trap. Yes. F of x equals 0 and f of x equals x squared both satisfy the equation. This equation right here. They both satisfy that equation. Except, let me clear some stuff just for the sake of it. Except, they're not the only functions that satisfy it. Any function that is equal to either 0 or x squared at every point satisfies these conditions. So what do I mean by that? So like, let's say we have some, here's an example, okay? So this weird looking graph right here. This looks like the ordinary f of x is equal to x squared graph, right? Actually, no. There's a random point right there just sitting around, and at every single point except for x equals -2, f of x is equal to x squared. But there's a hole right there, it's not right there, and it just goes down there. That does satisfy this equation, because at every single point except for -2, this term becomes 0, except when it is -2, this term becomes 0. So this is called the pointwise trap here. So we have to get out of it because we can't. Because the thing is that although this function that we have on this graph does seem to appear to work on our equation over here, it actually is not a solution to this functional equation when you plug it in. So how do we deal with this? So how do we deal with this is as follows, okay? So let's let A and B be non-zero numbers, okay? So let's make that clear. A is not 0. Wait, actually no. A and B are both not equal to 0, such that f of A is equal to 0 and f of B is equal to b squared. Why do we do this? Because what we want is we want to run into a contradiction here. Because what we want is that we want either f of x to be equal to 0 for all x, or f of x to be equal to x squared for all x. So if we can run in, if we say that a and b are in the same function and this is true, same function f and this is true, then that's bad. So that's why we want to run into a contradiction here, because proving that there can't be two numbers a and b such that this is true proves that these two will be our only two solutions. So now let's get going. Let's just get right to work. So we want to plug in x equals a and y equals b. What this gives us, let me create some little bit of space right here. What this does is that plugging in x equals a and y equals b, we get f of a squared plus b is equal to f of a, which is equal to 0. So, and then minus b. Oops, what was that? Oh gosh, this is a pain to erase. I have no idea how to erase that. Okay, yeah, so, actually, let me take that back. We want to plug in x equals a and y is equal to negative b, okay? So we get, instead, we get this is actually a negative right there. This becomes a positive. So, and then plus 4 times f of a, which is just 0, so that entire term just doesn't exist. So we also know that f of b is equal to b squared, so we'll write that down. We have f of okay. That's a nice, lovely equation, right? We got right there. Remember that b is not equal to 0. Remember that. That must mean that f of a squared minus b can't be equal to 0. Not it. But what does that actually tell us? This actually tells us that f of a squared minus b, if it's not 0, then it has to be a squared minus b squared, all squared. So, get rid of this random line that I have right there for no reason. We can equate these. Equating this, now we'll get to work on the where we have more space. We have b squared is equal to a squared minus b squared. This gives us a to the 4 minus 2a squared b is equal to 0, and a squared minus 2b is equal to 0. So going back, we also know that a is not equal to 0, okay? So that means that we can remove this a squared term, get rid of these parentheses, and we have our conclusion. A squared is equal to 2b. Very helpful. Let's go back. So this gave us the conclusion. This whole thing, plugging in x equals a and y equals minus b, this gives us the conclusion that a squared is equal to 2b. So, yeah, we have a squared is equal to 2b. Now what we want to do is that we want to plug in x equals a and y is equal to wait, I want to be careful here, sorry. Yes, so okay, yeah. So plugging in x equals a, and so so just now we just plugged in x equals a, and y is equal to minus b, okay? That's what we just plugged in. That was very messy. But, hold up. Why is PowerPoint not working? Okay, yeah, so, give me a moment. I think there's a slow error in what I've done so far. Okay, sorry. So, basically what's gonna happen here is that when we plug in x equals a and y equals b, we're gonna just get, f of a squared plus b is equal to b squared. Okay? Yeah, so this is what we're gonna get. So, when we plug in a and x equals a and y equals b. We know that from our previous time when we had x equals a and y equals minus b, we have a squared equals 2b, so we can just plug this in. And now we've actually ran into something similar to what we just did earlier. Since b is not equal to 0, then that means that f of 3b must equal 3b squared, all squared. So that means that this must equal 3b whole squared. But wait, so that means that by the transitive property, that 3b squared is going to have to equal b squared. But hey, that's only true when b is equal to 0. But we know that b is not equal to 0. So this is actually a visible contradiction here. There can't be a and b such that they're both not equal to 0, and they're part of different functions, or per se. One is part of f of x equal to 0, and other is part of f of x equal to x squared. So we ran into a contradiction here. So that means that that this whole thing, which we intended for it to be wrong, is all wrong. So that means our only solutions left if f of x is equal to 0 and f of x is equal to x squared, because these are the only two that do not have such points like this. So that's it. Thank you for listening to this lecture.